NASA sent a spacecraft straight into the path of an asteroid travelling at 14,000 miles an hour.
Well, scientists are closely monitoring an asteroid that is scheduled to pass Earth on December 24th. But mind you, this is no ordinary asteroid, but a gigantic one.
In 2022, NASA took a significant step by deliberately crashing a spacecraft into an asteroid, marking a key moment in the effort to protect Earth from potential threats. The mission, which aimed to test our ability to alter an asteroid's trajectory, appeared to be successful, at least at first. However, as time goes on, new questions are emerging. While the intention was to protect us, could this action inadvertently introduce unforeseen risks? The initial excitement over the achievement is now being overshadowed by growing concerns about the long-term consequences of altering celestial bodies. As scientists continue to analyze the results, these concerns are intensifying, and in this video, we'll delve into them in depth. Asteroid impacts aren't new. Asteroid impacts have long captured our attention, both scientifically and in popular culture. Often depicted as catastrophic events capable of instantly altering life on Earth, these portrayals stir a mix of intrigue and fear. This blend of curiosity and anxiety has fueled ongoing speculation about the chances of such impacts happening again. From massive craters to the fall of entire civilizations, the media has dramatized these scenarios, tapping into our collective fears and raising the question, could an impact of this magnitude happen again? And if it did, would humanity be prepared to prevent it? One of the most well-known asteroid impacts took place around 66 million years ago, with many scientists linking it to the extinction of the dinosaurs. This event remains one of the most significant in Earth's history, continuing to spark interest. However, the real question is how uncommon such impacts are. Could one like it occur again in the future? With millions of asteroids in space, the risk of a collision with Earth cannot be dismissed. Fortunately, scientists are already devising strategies to mitigate potential threats, including tracking, studying, and possibly redirecting these objects to avoid impact. Though it may sound like science fiction, it's an issue experts are beginning to take seriously. Asteroid impacts have played a major role in shaping Earth's history, from the creation of the Moon to the extinction of the dinosaurs. One of the earliest and most significant impacts occurred around 4.5 billion years ago during the formation of the Solar System. Scientists believe that the collision of a Mars-sized object, known as Theia, with the young Earth led to the formation of the Moon. This massive event had profound consequences, altering Earth's orbit, tilt, and even the composition of both Earth and the Moon. The enormous energy released from the collision would have caused Earth to melt and then re-solidify. The result, however, was a more stable planet, with the Moon playing a crucial role in regulating Earth's climate, tides, and supporting the development of life. Another significant asteroid impact in Earth's history was the Chicxulub event around 66 million years ago. This impact, caused by an asteroid striking what is now the Yucatan Peninsula in Mexico, is thought to have triggered catastrophic environmental changes, including massive wildfires, a global winter, and acid rain. These disruptions led to the extinction of roughly 75% of Earth's species, including the dinosaurs. The Chicxulub impact is often considered a pivotal moment in Earth's history, marking the beginning of a new era in which mammals, and eventually humans, began to emerge. While major impacts like the Theia collision or the Chicxulub event are rare, smaller impacts occur more frequently than we might think. Every year, Earth is struck by around 15,000 tons of meteors and space debris. However, most of these objects are small enough to burn up in the atmosphere before reaching the surface, resulting in harmless fireballs in the sky. The frequency of larger impacts has diminished over time. In the early days of the Solar System, there was more debris in planetary orbits, leading to more frequent collisions. As the system matured, many of these leftover bodies either collided with planets, were ejected, or settled into stable orbits, reducing the chances of larger impacts with Earth. Additionally, Earth's atmosphere now acts as a protective shield, burning up smaller objects before they can reach the surface. Still, the threat of larger impacts persists, and while these events are rare on geological timescales, their potential consequences are so severe that scientists are developing advanced technologies and strategies to monitor space debris. These efforts are vital, as the effects of large asteroid impacts can be devastating, causing widespread environmental damage and threatening life on Earth. The ongoing study of past impacts, combined with new monitoring technologies, is crucial not only for understanding Earth's history but also for preparing for possible future collisions. While such an event isn't an immediate concern, it remains a reality that we must continue to face. Asteroids have been crashing into Earth more than you think. Meteor data and statistics emphasize how often Earth encounters space debris and the potential dangers these impacts pose. Small meteors, ranging from the size of a grain of sand to about 40 centimeters in diameter, strike Earth daily. In fact, roughly 25 million of these tiny meteors enter Earth's atmosphere each day. Most burn up upon entering, creating visible streaks of light known as shooting stars, or meteor showers. Due to their small size, they generally pose no threat to Earth or its inhabitants. However, larger impacts, although less common, present a greater risk. Each year, about 4-meter-sized objects enter Earth's atmosphere. While these meteors are large enough to cause significant damage if they hit populated areas or critical infrastructure, such events are rare. Nevertheless, the potential for regional destruction makes monitoring space debris a priority for space agencies worldwide. Even larger asteroids, ranging from 100 meters to several kilometers in diameter, strike Earth much less frequently. An asteroid about 100 meters in size hits Earth roughly once every 2,000 years. When these asteroids collide, their immense size, high velocity, and the energy released can result in widespread regional destruction. These impacts could cause powerful explosions, fires, and massive shockwaves that devastate entire regions. While rare, the severity of such impacts warrants ongoing research and monitoring. Asteroids larger than 10 kilometers, which have the potential to threaten civilization, are extremely rare. These enormous objects could cause global disruption, potentially triggering climate change, mass extinctions, or even the collapse of human civilization. Thankfully, tracking systems have become highly accurate, allowing for reliable detection of asteroids of this size or larger. Through continuous monitoring of near-Earth objects and the use of advanced technology, space agencies like NASA have made significant strides in detecting and understanding these threats. While many of these objects simply pass by Earth, we aren't always so fortunate. The Chelyabinsk meteor. The Chelyabinsk meteor, which exploded over Russia on February 15, 2013, is a powerful reminder of the potential consequences of smaller asteroids. While it wasn't large enough to cause global devastation, the event highlighted how even a relatively small asteroid, around 20 meters in diameter, can inflict significant localized damage. The meteor exploded in the atmosphere, releasing an estimated energy equivalent to 470 to 500 kilotons of TNT. The shockwave that followed damaged over 7,200 buildings, including schools, hospitals, and homes. Thousands of windows were shattered, sending glass shards into the streets and causing numerous injuries. Around 1,500 people were hurt, mostly due to the broken glass and debris scattered by the shockwave. What makes this event particularly significant is the extent of the damage caused by a relatively small asteroid compared to much larger, civilization-threatening ones. Despite its smaller size, the Chelyabinsk meteor's effects were profoundly felt on a regional scale. The explosion, though not fatal, demonstrated how even an asteroid of this size could cause widespread disruption in populated areas. The incident highlighted the local risks posed by smaller, less detectable objects. While asteroids and meteors of this size are common, they can still have a serious impact, especially in densely populated areas. It also revealed shortcomings in tracking and early warning systems for smaller objects, despite advances in monitoring larger threats. As a result, the Chelyabinsk meteor prompted a global reassessment of detection systems. Tracking systems. Over the past 2 decades, significant progress has been made in tracking and monitoring asteroids. Astronomers have identified over 20,000 potentially hazardous asteroids, representing a major step forward in understanding and assessing objects that could threaten Earth. On average, approximately 30 new near-Earth objects are discovered each week, demonstrating the rapid advancement of monitoring systems. These efforts focus primarily on detecting asteroids large enough to cause damage and close enough to cross Earth's orbit. By analyzing their movements and sizes, scientists can assess their risk and devise potential mitigation strategies. However, detecting smaller asteroids remains a challenge, as their reduced size and dim visibility make them harder to spot against the vast backdrop of space. Many go undetected or are only discovered after entering Earth's atmosphere, as seen with the Chelyabinsk meteor. Since smaller asteroids are more common, improving their detection capabilities is equally critical. Several close calls have emphasized the need to enhance systems for identifying these elusive threats. To address this, scientists are improving telescope technology and employing both space-based and ground-based observation platforms. Advanced tracking systems, such as NASA's NEOWISE mission and the Pan-STARRS Observatory in Hawaii, are actively scanning the sky for new potential threats. Additionally, international collaboration among space agencies has bolstered efforts to detect and track asteroids that might be on a collision course with Earth. Despite the significant advancements in detection, it remains essential to identify and understand the full spectrum of potential hazards, from the largest to the smallest. Early detection is crucial for mitigation, as it could provide the time needed to prepare for or deflect a possible collision. This is where missions like DART play a vital role. The DART test. The DART, Double Asteroid Redirection Test, mission marked humanity's first attempt to alter an asteroid's trajectory as a proactive measure against potential future threats. Launched in November 2021, it was a groundbreaking moment in planetary defense, designed to demonstrate that technology could effectively prevent a catastrophic asteroid collision. DART targeted the binary asteroid system Didymos, specifically its smaller moonlet, Dimorphos, as the impact site. Although Dimorphos, measuring approximately 160 meters in diameter, posed no threat to Earth, it was an ideal test candidate. The mission involved deliberately crashing a spacecraft into Dimorphos to alter its orbit around Didymos, testing whether a kinetic impact could successfully redirect an asteroid's path. This ambitious initiative was a collaborative effort involving several space agencies. NASA led the mission, with the Johns Hopkins University Applied Physics Laboratory managing the project. Additional support came from Italy, Japan, and other European space agencies, underscoring the global nature of planetary defense and the collective effort to address a shared existential risk. The primary objective of DART was to validate the kinetic impact technique, using a high-speed collision to change an asteroid's trajectory. If proven successful, this method could become a cornerstone of planetary defense strategies, enabling humanity to redirect potentially hazardous asteroids before they pose a danger. While this approach may appear drastic, it is one of the few practical options available for averting a potential impact. Following extensive evaluation of alternative methods, asteroid deflection. Before the DART mission, scientists and engineers explored various asteroid deflection strategies, many influenced by fictional depictions, such as the dramatic scenarios in the 1998 films Armageddon and Deep Impact. These movies showcased high-stakes methods like drilling into an asteroid to plant explosives. However, real-world science emphasized more controlled and gradual approaches, given the immense scale and complexity of deflecting objects traveling through space at extraordinary speeds. One proposed strategy involved space harpoons, where spacecraft would deploy large, durable harpoons to anchor onto an asteroid's surface. This attachment could then allow controlled force to redirect the asteroid's trajectory. However, this idea faced numerous hurdles, including the unpredictable nature of an asteroid's surface, whether rocky, loose, or metallic, and the difficulty of approaching a fast-moving object. Additionally, generating sufficient force to alter the asteroid's path without fragmenting it posed another significant challenge. Another concept focused on laser ablation, which proposed using high-powered lasers to heat the asteroid's surface. This would cause material to vaporize, creating thrust in the opposite direction and gradually shifting the asteroid's orbit. Although promising for its precision and control, this method also encountered technical obstacles. It required incredibly powerful lasers and advanced targeting systems capable of operating across vast distances in space. Furthermore, questions remained about its efficiency and the feasibility of generating the necessary energy without significant loss over such distances. While these ideas were largely theoretical due to the lack of necessary technology, they sparked valuable discussions and helped shape the field of planetary defense. They also encouraged innovation and the pursuit of practical solutions for mitigating asteroid threats. With DART's success as a kinetic impactor, these earlier concepts remain an inspiration for future research and could one day complement proven methods like the kinetic impact approach in planetary defense strategies. Other ways to deal with the problem. Before NASA's DART mission successfully demonstrated asteroid deflection, a variety of strategies were proposed to prevent catastrophic impacts. These ideas range from leveraging gravitational forces to deploying high-tech lasers or even nuclear detonations. While innovative, each approach faced unique challenges and uncertainties. One proposed method was the gravity tractor, where a spacecraft would hover near an asteroid and use its gravitational pull to gradually alter the asteroid's orbit. Without landing on the asteroid, the spacecraft would perform precise maneuvers to create a slow but steady shift in its trajectory. Although theoretically feasible, this method required a significant amount of time to produce results, making it impractical for short-notice threats. It relied heavily on early detection to provide the extended time frame needed for the deflection. A more drastic idea involved detonating a nuclear device near the asteroid's surface to change its course through the force of the explosion. While potentially effective, this method came with considerable risks, particularly the possibility of fragmenting the asteroid. If the explosion caused the asteroid to break apart, the resulting debris could still pose a threat to Earth, potentially creating multiple impacts instead of averting disaster. These risks, combined with the technical complexity of executing a precise detonation, made the nuclear option highly controversial. Another concept involved using large space-based mirrors to concentrate sunlight onto an asteroid's surface. The intense heat would vaporize material, creating a jet of gas that could gently push the asteroid off course, a process known as outgassing. While this approach offered continuous propulsion without requiring physical contact, it faced significant logistical and technological hurdles. Building and deploying massive mirrors in space and effectively focusing sunlight over vast distances remained speculative, with no existing technology capable of executing this plan. These proposed strategies illustrate the diverse and creative solutions scientists explored prior to DART. However, the challenges and uncertainties associated with each highlighted the complexities of planetary defense. The DART mission's practical demonstration of a kinetic impact provided a more realistic and actionable approach, making it a pivotal step forward in protecting Earth from potential asteroid threats. Selecting the asteroid. The primary goal of the DART mission was to demonstrate the feasibility of asteroid deflection as a planetary defense strategy, specifically by testing the direct kinetic impact technique. This approach involves sending a spacecraft to collide with an asteroid at high speed to alter its orbit. The mission aimed to validate this method as a viable means of diverting potentially hazardous asteroids from Earth. For the experiment, NASA selected Dimorphos, a small asteroid, or moonlet, within the binary asteroid system it shares with its larger companion, Didymos. In this system, Dimorphos orbits Didymos in a stable gravitational relationship. Dimorphos was chosen due to its size and characteristics, which made it an ideal target for the test. Measuring about 525 feet in diameter, it was large enough to serve as a realistic target for deflection experiments, but small enough to ensure that any changes to its orbit would not pose a risk to Earth. At approximately 6.6 million miles from Earth during the mission, the asteroid's relative proximity and safety made it a perfect candidate. Additionally, its location within a binary system ensured that any alterations in its trajectory after impact could be monitored without endangering our planet. Another key factor in selecting Dimorphos was its straightforward orbital dynamics. While it poses no threat to Earth, its orbit around Didymos made it an excellent subject for precise observation using ground-based telescopes. This setup allowed scientists to track even subtle changes in Dimorphos's motion. The mission's objective was to observe how the DART spacecraft's kinetic impact affected Dimorphos's orbit around Didymos, with particular focus on measuring changes to its orbital period. The experiment sought to determine whether a single, carefully planned collision by a spacecraft could effectively alter an asteroid's trajectory. If successful, the results from Dimorphos would provide critical insights into the use of kinetic impact as a planetary defense strategy. The data gathered would form the foundation for future efforts to prevent asteroid impacts on Earth. One significant challenge was the relative smallness and faintness of Dimorphos compared to other celestial objects, which made tracking it difficult without high-powered telescopes. However, its status as part of a binary system with the larger, brighter Didymos helped mitigate this issue. The orbital relationship between the two allowed for precise monitoring of Dimorphos's movement, enabling scientists to measure the impact's effect with high accuracy. Selecting Dimorphos for the DART mission provided a safe and scientifically valuable opportunity to test planetary defense capabilities. The results from this experiment hold the potential to revolutionize how humanity addresses asteroid threats. With the target secured, preparations for the spacecraft's historic journey began. The spacecraft. The DART spacecraft was a compact, refrigerator-sized vehicle weighing approximately 1,340 pounds, specifically engineered for the precise task of altering the orbit of Dimorphos through a kinetic impact. Despite its modest size, DART's advanced design ensured optimal performance for its mission of asteroid deflection, with a streamlined structure tailored for space operations. A standout feature of DART's design was its payload, which included the Draco camera. This high-resolution camera, short for Didymos reconnaissance and asteroid camera for optical navigation, was integral to guiding the spacecraft to its target. Draco captured real-time, high-definition images of Dimorphos, enabling accurate navigation and course corrections. It also monitored the surrounding space environment to avoid obstacles, ensuring the spacecraft maintained a clear path to its target. In addition to the main spacecraft, DART carried a secondary payload, LICI-Cube, Light Italian CubeSat for imaging of asteroids, developed by the Italian Space Agency. This small, 12-inch, 14-kilogram CubeSat was deployed just before impact to document the collision's immediate aftermath. LICI-Cube captured data on the changes to Dimorphos's surface and the ejected material, known as a diverted ejecta plume, providing crucial insights into the mechanics of the impact and its effectiveness in altering the asteroid's trajectory. Together, DART and LICI-Cube formed a complementary system designed to achieve the mission's objectives and gather critical data for future planetary defense efforts. Though its appearance was simple, DART's capabilities were cutting-edge, with Draco and LICI-Cube working in tandem to ensure mission success. However, traveling from Earth to an asteroid over millions of miles was no straightforward task. A critical component of DART's mission was the Smart Nav system, small-body maneuvering autonomous real-time navigation, which enabled the spacecraft to autonomously target Dimorphos with exceptional precision. This system allowed DART to navigate independently, particularly during the final approach phase, adjusting its trajectory in real time to account for any unexpected factors or errors. SmartNav relied on advanced sensors, including star trackers and an onboard computer, to continuously map the spacecraft's surroundings, compare its position to the target, and make necessary course corrections. Approximately 1 hour before impact, SmartNav assumed full control of DART, executing precise adjustments to ensure the spacecraft hit Dimorphos at the optimal location and angle. This autonomy was essential, as manual control from Earth was impossible due to the vast distances involved. The successful deployment of SmartNav marked a significant milestone in autonomous navigation for space missions, paving the way for future applications in planetary defense and asteroid redirection. With all systems ready, the mission advanced toward its ultimate objective. The launch. The DART mission launched on November 23, 2021, aboard a SpaceX Falcon 9 rocket, embarking on a 10-month journey to its target asteroid, Dimorphos, within the Didymos binary system. Throughout its mission, DART was closely monitored, with mid-course corrections ensuring its trajectory remained accurate. In the final 90 minutes before impact, As the spacecraft neared its target and was approximately 24,000 kilometers away, it executed its last approach adjustments to align precisely with Dimorphos. During this critical final phase, the Draco camera aboard DART captured real-time images of Dimorphos and Didymos. These images were essential for navigation and provided detailed insights into the asteroid's shapes, sizes, and surface features, ensuring the spacecraft's approach and impact were meticulously fine-tuned. On September 26, 2022, DART successfully collided with Dimorphos, achieving the mission's primary objective of altering the asteroid's orbit. This marked the first successful demonstration of changing an asteroid's trajectory via kinetic impact. Traveling at a speed of approximately 14,000 miles per hour, DART's collision significantly shortened Dimorphos's orbital period around Didymos. Pre-impact, Dimorphos completed its orbit in roughly 11 hours. Post-impact, observations confirmed a reduction of about 33 minutes, validating the effectiveness of the kinetic impact technique for asteroid deflection. This milestone experiment showcases the potential of the kinetic impactor method as a practical planetary defense strategy. By altering an asteroid's velocity and trajectory, this approach offers a non-destructive means to prevent potential collisions with Earth. While Dimorphos was chosen as a safe test target, the mission's success lays the groundwork for responding to future asteroid threats. The DART mission represents a significant advancement in planetary defense, demonstrating humanity's ability to track, intercept, and redirect hazardous space objects. This achievement could play a critical role in safeguarding Earth against asteroid impacts, forever changing how we approach planetary defense strategies.